interrupt me. So this is a talk this is a talk on behavioral relations, equivalences, and preorders. Intuitively, two terms are equal if no difference can be observed by interacting with them. Now, the notion of interaction is usually expressed by means of label transition systems, where transitions are of these forms. This P is the initial term. I will call them processes in this talk. P is performing an interaction with its environment, where the contribution from P is this action mu, and P prime is what P becomes after performing such interaction. The formalization of the meaning of equality of behavior has produced a lot of debate and a lot of proposals throughout the years. These proposals differ in the way in which observables are taken into account. So the difference among them is concerns what can be observed of the behavior of the processes. But roughly, we can distinguish between the inductive relations and the coinductive ones. The inductive relations are relations in which the observables are intuitively inductively defined. The simplest such relation is the trace preorder, whereby P is below Q if all traces of P are also traces of Q. Now, the trace preorder is usually often considered a little bit too coarse. It does not have good properties with respect to deadlock, for instance. So people have put forward finer notions. Among these, a prominent one is the failure preorder, introduced and popularized by Tony Hoare and people in his group, where the observables are failures, and the failure is a pair of a trace and a set of action that the process, after performing that trace, is unable to execute. And there are many other inductive preorders, for instance, the ready preorder, the failure trace preorder, the ready trace preorder, and so forth. Among the coinductive ones, one of the best known is certainly bisimilarity. It is widely used, it is mathematically robust, it has an elegant proof method, and furthermore, this proof method can be enhanced. And the enhancements of the bisimilation proof method are the starting point for this talk. This slide reminds you what is the bisimilation proof method. So if you want to prove two processes bisimilar, I will use the term processes here for the terms of the language one is interested in, but the language need not be a language of processes. So if you want to prove two processes bisimilar, we have to find a bisimilation containing them as a pair. And what is a bisimilation? Well, it is a set of pair of processes that can mimic each other action in this challenge-response game in such a way that the derivatives, the final derivatives, are again in the original relation R. Now, this method is very elegant, powerful, yet sometimes it is hard to use because the bisimilation can be very large, to the point that sometimes it may even be hard to define or describe them. And one of the main culprits for this is the requirement that the final pair of derivatives at the end should be a pair in the relation R itself. This can be a frustrating requirement, sometimes in proofs, where one tries to start from a bisimilation candidate, a candidate relation at the beginning, hoping that this is indeed a bisimilation. Then one goes on and checks for this challenge response game, perhaps to find out that there are some pairs that are needed that are not in the original relation, so they have to be added. And then the checks have to be repeated, and perhaps one finds other pairs that have to be added, and so forth. And maybe sometimes it is even harder to find out, to understand which pairs have to be added. So for this reason, enhancements have been introduced. In fact, the first enhancement, called the bisimilarity, has been introduced by me shortly after having introduced bisimilation. And in this enhancement, it is sufficient that the two derivative processes at the end are bisimilar to processes that as a pair are in R. Throughout the years, many more enhancements have been introduced. For instance, a powerful one is the bisimilation up to context, where in the derivatives at the end, if there is a common context, this context can be cut off. insufficient, what's left are processes in R. Most important, the enhancements can sometimes be composed. This is an example in which I'm composing the 2 plus 1 in violation and context. So using enhancement, the challenge and response game of bisimulation becomes something like this, where you start from a given relation R and you end up with derivatives that are in another relation f of R, where f is a function from relations to relations. I will use this notation and the progression to mean a response game like that between a certain relation and another one. Of course, such an enhancement is interesting if R is smaller than f of R. In fact, the smaller R is, the better the better is, in the sense that the enhancement is more powerful and more interesting. Of course, not any function can be used for this. We can only use the functions that are sound, meaning that sound if whenever there is a progression of this kind, then indeed the pairs in R are also pairs of bisimilar processes. Each function is a bisimulation enhancement. Over the past 2 decades and more, simulation enhancement have been developed. In particular, algebra of enhancement have been proposed with the goal of deriving for free sophisticated enhancement one by using appropriate constructor for composing enhancements. Now, for this purpose, the set of sound function is not enough. It does not have good compositionality properties. So people have looked at subsets of sound functions with better properties. For instance, the respectful function, the compatible function, where the main key requirement is that the function itself has a progression. So if you have progression from R to S, then also you have that progression, well, another progression from FR to FS. There are people who have also devised abstract formulations of enhancements. We have heard about this invited to by example before. For instance, formulations using category theory, algebra, but also more is fixed point theory. Now, bisimilarity, however, has also some drawbacks. One of the major criticisms is that it is too fine, in the sense that it sometimes distinguishes many processes. This is an example. So suppose that we want a process that non-deterministically outputs at C one of the 2 values received at A. And now this is the behavior of possible implementations of this spec. On the left, the non-deterministic choice is made before the input at A is performed. On the right, the non-deterministic choice is made after the input. There is this difference in concerning the moment when the non-deterministic choice is made. However, from a client perspective, so from the point of view of somebody interacting with these systems, difference is completely irrelevant in the sense that there is no way for the client, when interacting with the system, to understand, to figure out whether he or she is on the left or with the system on the right. Accordingly, we would like to consider these 2 implementations equivalent, but in fact they are not bisimilar. They're not bisimilar because intuitively bisimilarity is sensitive to the branching struct of the LTS to the point where the deterministic choices are made. So against the problem, people propose the use of inductive equivalences. In fact, under trace, failure, or ready equivalences, the inductive relations that I mentioned before, these 2 systems are equal. Another major drawback of bisimilarity is that it does not have a natural associated reorder. So, for instance, we might like to have Reorder to say that the 2 non-deterministic systems that I have described earlier in the previous slide are related to a system that systematically outputs at C the first of 2 values received at A. So this is deterministic. And the use of a reorder here can be useful because it allows us to say that the behavior on the right is richer. It has more possibilities. So this kind of formalization is not possible using bisimilarity because it is not the kernel of a natural pair. People advocate the use of inductive relations, actually defined as preorders, and then the equivalence is taken as the kernel of such preorders. Despite these problems, for bisimilarity, often people prefer and like to use bisimilarity precisely because of the possibility of exploiting the bisimulation enhancements. Now, the goal of the work that is reported in this paper is to try to transport the theory of bisimulation enhancements to the realm of inductive behavioral relations. So first of all, I have to define formally what is an inductive preorder, more precisely what is an inductive observable. For this, I have used a modal logic namely the positive fragment of any similar logic, in which we have the operators of diamond. So a process satisfies mu theta if the process can do an action mu, the derivative p prime can then satisfy the remaining formula theta. And then we have functions. This is an unitary conjunction. It can also be empty, in which case we have the formula true. I also have atomic observables, but for the purpose of this talk, we can safely skip them. A formula from this logic intuitively represents an observable, so a piece of behavior that we want to observe. So for instance, this diamond A, diamond B formula intuitively allows us to observe the possibility of performing the trace AB. And this formula here intuitively allows us to check the possibility of, and then at the end, a situation in which both C and D are possible. So any subset of formulas from this model logic yields a preorder, namely the preorder in which a process is below another one, observables for the first, but also for the second. So this is the meaning of inductive preorder. Preorder that can obtain in this way using formulas from this. In the remainder of the talk, I will skip this script O in the symbol for preorder because it's clear from the context. This O is the set of observables. So here are some examples. The preorder we obtained using just the diamond, the formula, and then you need a little more atomic observables for failure rates, and so forth. There's nothing here. These are the standard model logic characterizations of such preorder that exist in the literature. Now, the second step is to now define the enhancement for such orders. And for this, I need a number of approximants of weight level, if you want. I will describe this intuitively. I think it will be sufficient. Intuitively, at weight n, so at level n, at the approximant n, we only allow to observe transitions emanating from a process up to a depth at most n. So, for instance, in the nth approximant of the trace preorder, we can only observe traces or processes of length at most n. By having approximants, then the preorder itself can be obtained using the intersection over all the approximants. Now, the key step is a definition of the function of inductive enhancement. So for this, I follow the scheme of simulation enhancement progressions. In fact, here I need semi-progression because we are working with preorders. So we only the challenge response gain in one direction from right. So a function relations is sound for a given preorder if whenever there is a semi-progression of this kind, then indeed the pairs in R are also pairs in the preorder. Okay, so now the objective, what is the objective, is to isolate a subset of sound function that is rich enough to contain interesting functions and to yield each algebra, an interesting algebra. I'm talking about algebra because we are very much interested in composing enhancement, much in the same way as we do it with bisimilar enhancement. So for this, I pose a notion of weight-preserving function or approximate-preserving function, a function such that whenever a relation R is in the nth approximant, then also f of R is in that approximant. This is the meaning of weight-preserving function. Theorem, if f is weight-preserving for a given preorder, then f is also sound for that preorder. And this is a theorem that is proved, as one can well imagine, by relying heavily on induction. Now, the set of weight-preserving functions yield an algebra that has similar to the algebras that we find in the literature for bisimulation enhancements. So one can, for instance, use constructors for composing enhancements, such as function for relational composition, union, and so forth. This example of a derived enhancement, this is analogous of the bisimulation up to bisimilarity in context enhancement that we have seen in earlier slide. So in this case, we have the preorder, the inductive in place of bisimilarity. In the paper, most of the theory about inductive enhancements is carried out in a way that is parametric on the preorder and on the language of terms one is interested in. with one important exception, the up-to-context function that is both language and preorder dependent. And in the paper contains a preliminary study of this up-to-context function and of its soundness. In the paper, you also find some, well, kind of reasonably large examples of application of the inductive enhancements in a language that is a process language CCS-like. In particular, you find the results improved that are parametric on the preorder and on the term language. An example of such a result is the substitutivity for recursive definition. This result for a given preorder says that if you have two terms E and F of your language, one below the other one, and they may contain the free variable x, then also rec x E is below rec x F. This kind of properties, this substitutivity for recursive definition, in the case of behavior of inductive preorder, are sometimes delicate to prove. Using inductive enhancements, one can give a general proof that is parametric, and the general theorem says that whenever you have a preorder and a term language in which the up-to-preorder function is sound, then you have the substitutivity property. You find in the paper also some proof that revisit proofs in the literature about inductive preorders that have stratification, that involve stratification. These proofs are revisited as applications of these inductive enhancements. I conclude with a few points of further and future work. I have not discussed in this short talk the difference between strong and weak semantics. This is a relevant and important difference. In a strong semantics, you observe all actions in the same manner. In a weak semantics, you try to abstract away from internal actions. So in the challenge response game, the response part can make use of as many internal actions as needed. This difference has important consequences on enhancements, both in the case of bisimulation and in the case of inductive enhancements in this paper. There is a study of this that you can find in the paper, and there is more to be done there. Most important, abstract formulations. I've mentioned before, and we've seen in Alexandra Silva's talk, that by simulation and conductive enhancements have been given abstract formulations using category theory, fixed point theory, and so forth. I'd love to see and to know what is the analogous for the kind of enhancements that I have proposed in this paper. A final point about up to context. In the case of by simulation enhancement, up to context has been shown to be that can be used to derive congruous properties for the operator of the language. I believe something like that can also be done in the case of inductive preorders, so to obtain congruence results for precongruence results for these preorders using the soundness of the up to context. So I stop here. I think I've used all my time.
We should thank Davide. Okay, so as a reminder, I'm sure nobody needs to be reminded that Enhancement exists, and if you've got any questions, you can put them onto the Q&A in Enhancement, or I can take them live if anybody's got questions from the room. Anybody in the room? Okay, do we have anything? Okay, do we have anything on? Okay. In which case, I've got a question for Davide. I've got a question for Davide, which is the presentation of inductive refinement that you gave here was based on observables, whereas the co-inductive definition was differently motivated, differently defined. So I was wondering whether, what's the commonality between the co-inductive and the definition of co-inductive and inductive relation?
Well, the kind of commonality in the enhancements that I've derived, the most obvious commonality is the fact that I start off from this notion of progression or semi-progression progression in both cases. Then there is, of course, a striking difference in the sense that I have somehow to take into account the inductive nature of the observables for the inductive relations. And I struggled a lot in order to try to figure out what is the best way for doing that. And this is how, and at the end, I ended up with this idea of exploiting a model logic and observables defined from the model logic. And then I try to, of course, integrate these into this business of progression and semi-progressions. I should make another comment here. Why do I use progression and semi-progressions? Well, there is one important reason for that, which is this. One of the key ingredients of the bisimulation proof method and its enhancements, and one of the reasons for why people find it useful, effective, is that the checks that one has to make on processes are local. So there is this challenge response game, and the transitions that one has to check are local to the processes in the pair. You check only the immediate transitions emanating out of the processes. So for instance, you do not check traces of transitions, which would be a non-local requirement. Okay, so I've tried very much to maintain this locality property in the enhancement for the inductive preorders, which is this is of course contrasted with the fact that the inductive preorders are naturally defined on top of observables that are not local. You know, there are traces or enriched form of traces. And this is also the reason for why I find it difficult currently to understand and figure out what is the best formalization abstractly of the techniques that I presented using, you know, even without referring to category theory, just simply fixed point theory. It's not easy because on the one hand, I use this kind of progression that refer naturally to the coinductive world. On the other hand, there are these traces and the inductive defined observables that refer to the inductive world, not the coinductive one.
Thank you very much. Okay, I think we should thank Davide again.
Thank you.